Okay, so welcome back to the lectures. So today we are going to explore the mathematical aspects of the phase field crystal model. So it's quite important because if you want to get like thermodynamics property out of this phase field crystal modeling, you need to carry out certain calculations. So during the lecture, if you have any question, don't hesitate just to stop me and let me know if you have any questions. Okay, so I'm going to start with the evolution equation. We know it is a conserved dynamics. So that gives us like two control parameters for the phase field crystal, right? And from there, I'm going to show you possible phases for the phase field crystal and how we calculate the energy for each phases. And with this energy of each phases, then we can determine whether they can be coexist with each other, or if I just set certain parameters, which phase will be the ground state for that set of parameters. So things like that. And we are also going to answer the question why you are expecting to get a 2D hexagonal lattice as a ground state, not like square lattices, or why you are expecting to get this BCC as a ground state in the 3 dimensions. So there is some work you need to do extra in order to get other crystal structures in 3 dimensions. For example, if you want to get like a FCC structures, you have to use a multi-mode method to get that. But there's a fundamental reason why you don't expect to get something else in 3D. So that's something we are going to talk about today. And in addition, I'm going to talk to you about 2 additional ways to model the phase field crystal system. You can either try the non-local conserved dynamics if your problem is, or if you only concern about the equilibrium property of your material system, you don't really care about the kinetics, how the system reach the final equilibrium state. So if that's the case, you want to speed up your simulation, you can choose to run a non-local conserved dynamics. Or in certain cases, you don't really want your system to be like the number of parts, you don't want that to be conserved. For example, if you want to do a solidification problem, you can use a grand canonical ensemble, which means you just fix the chemical potential and the particle can flow in, right, during the solidification. Okay, so those will be the topics we are going to cover today, all right? Okay, so first, we have seen these slides several times, so roughly now you probably have some idea why the system prefer to select specific wave number, right? Because this Laplacian plus 1 square kernel, intuitively, the system is going to pick up the density waves for which the magnitude of the wave number or the wave vector to be 1. So when you plug those in, you got this -1 plus 1, the whole thing squared, basically. It's going to minimize the free energy. And for the nonlinear competition, we are going to talk about that later because I'm going to show you why in 3 dimensions the FCC structure is always a metastable state for this type of phase field crystal. I mean, for this kind of free energy functional, right? So in other words, if you want to get FCC, you have to modify the free energy just a bit. If we have time, we'll cover that as well. Okay. So the phase field crystal, we use this conserved dynamics. So basically, we are expecting psi bar is a conserved quantity, right? Because the conserved dynamics, you don't expect the mean density change over time. So in a sense that you can actually control both epsilon, the value of epsilon, and also psi bar. So you have 2 parameters that you can control for your phase field crystal modeling. And first, I'm going to show you that if you are running this kind of conserved dynamics, and the energy or this function f can only decrease monotonically over time. All right, so something you probably have already seen that in the phase field model. You probably have done the derivation. Just let me do that quickly for you for the in this case. So if I want to find out how this energy F is going to change over time, of course, I'm caring about the quantity dF over dt, right? So for a unit time dt passed by, how much the energy is going to change, that's my dF. So since my free That's not called that free energy in for now. Let's just call this a function f, right? So the function f is it is a functional of the density field per psi, but per psi also changes with time, right? So in order to get df/dt, you have to carry out this to check out how the f changing over different profile per psi, and also times how the per psi changing with time. All right, quite straightforward. But actually, you are seeing this partial per psi partial t somewhere, right? It's from the evolution equation. So you can do a substitution, just plugging this partial per psi partial t right here. So what you are getting here is actually the first term doesn't change, but the second term become just the del f delta per psi and taking Laplacian. Right, I just plug in whatever the evolution equation is telling me to this df dt. And the typical trick is to do an integration by parts, right? So you can check this identity that you can write this del f del phi times the Laplacian del f del phi into those two terms. All right, that's quite standard trick you do. But now if you look at the first term, right, the first term is something take the divergence in doing an integral. So you know we are going to use the divergence theory to argue that the first term is going to vanish. And the reason is that, for example, in our simulation, we are using the periodic boundary condition. So which means if you're using the divergence theory, this term is going to count what would be the net flux coming in and out of the surface, right? The net flux through a surface. But now if I'm using a periodic boundary condition, which means I'm cutting a surface, but it's periodic boundary conditions. So whatever comes in equal to whatever comes out to the other end. So just through that concept, you know the first term, the total flux on the surface is going to be 0. So through divergence theory, we know we can drop the first term. So we only have the second term left, which is something square. It's the del f del per psi, take a gradient, the whole thing square. So there's a negative sign in front. So we just showed that with this kind of conserved dynamics, f can only decrease monotone over time. So we are actually carrying out a process. The system is going toward, is evolving toward a direction that minimize f function here. So that's something we are quite familiar with in the thermodynamics, right? Because we call that kind of function is sort of free energy, right? So I'm still using like Helmholtz free energy here, but later on I'm going to give you more clue or try to justify. Actually, in this case, F is the Helmholtz free energy of the system, right? But at this moment, you can take F is a kind of free energy, right? And we know per psi bar is a constant, which means if you do an integral over volume, which means you fix the volume and also number of particles fixed. So we know it's an NV some ensemble. And if we interpret epsilon as the temperature, then it seems like a canonical ensemble to me. Right? So F could be the Helmholtz free energy. All right, so what's next we are having here is that since per psi bar is a conserved quantity and epsilon is something we choose, and we are not going to change that during our simulation, so the system actually have two free parameters that we can set for each simulations. So instead of like, okay, so the next question is that we are going to see how the system, the behavior of our system or the behavior of our simulation, how does that change with different set of those two parameters, right? We can vary epsilon, we can vary per psi bar, but how the system is going to respond to those changes. All right, any question so far? Good. All right. Okay, so let me just show you the result first, right? Of course, here is the phase diagram of the 3D phase field crystal. So as I just telling you that you can choose a pair of the parameters, right? So if you are choosing like per psi bar and epsilon somewhere here, you are expecting to get a liquid state. So depends on the parameter you are choosing, you can get different phases. The shaded area here corresponding to a coexistent region. So if you are choosing the epsilon and per psi bar somewhere in between, in this shaded region, you are going to, for example here, you are going to have this BCC liquid coexistence. So here I'm going to show you one example what the PFC simulation looks like here. So if you choose the parameter over here, you run a simulation, you get this three-dimensional BCC structure. And if you do an analysis, you will find out that the density description can be well approximated by this simple summation of the density waves. So since we are talking about the BCC structures here, the density can be well approximated by the summation of the density wave of the principal reciprocal lattice factors. So for BCC, you know the principal reciprocal lattice factors are the FCC lattices, which means all the combination of either 110 or 101 or 011 or -101, things like that. You have all the 12 reciprocal lattice factors. So if you just sum all 12 of them and setting the amplitude to be the same, because in solid, the amplitude for different density waves, they should be the same because it's isotropic. So if you just do a simple summation, you can get this BCC structure. And in the phase field crystal simulations, if you are really close to the phase boundary, like here, this approximation is actually a very good approximation. And the reason for that is that if you remember, we talked about the linear instability a little bit yesterday, right? So I hope that you still recall that there is like an inverted kind of concave parabola kind of instability curve, right? So if the control parameter or the epsilon here we choose is very close to the onset of instability, which means you have this parabola, right? But only a very small range of the wave number can be excited, which means the growth rate for very tiny window of k are positive. So which means you are expecting the wave number that can be excited is roughly or exactly equal to 1. So you are not expecting something else to be excited. But however, if you are expecting like the solid here to be very localized, for example, like a delta function or over Gaussian profile. But you know, in order to have this narrow Gaussian localized profile, when you do a Fourier transform, you are expecting to have a lot of different wave factor in order to get that kind of structure, right? But in the PFC, what we are talking about here is just right around the onset of instability. So the system don't have those many different wave numbers for you. So that's why you are expecting that just with a single mode, just the principal reciprocal lattice factors, it is good enough to describe these BCC structures in PFC. All right. So this kind of approximation is something we are going to use later in our calculation. So what I'm saying here is that usually in the phase field crystal, when we do analytical calculations, we would assume the solid density is some mean density per psi bar, but plus a summation of the density waves. But how many density waves we are considering? We only consider the principal reciprocal lattice factor. That's it. All right. So for BCC, you have 12 reciprocal lattice factor. Like for 2D hexagonal lattice, because the 2D structure, you are expecting like only 6 density waves, right? With the K, that will be 60 degrees apart around the circle. All right. Yeah. Yeah. You mean there's a hexagons in BCC, right? Yeah. So so if we are talking about atoms, right? So there is no correspondence for this hexagonal face in material size or in these atom-like pictures. So those are not realistic if when we talk about the QSIS modeling of like the solid liquid interfaces. But they have certain application in polymer physics. You do have this laminar structure they can arrange in like hexagonal symmetry, things like that. So for our purpose, we mainly focus on the BCC liquid here. Yeah. All right. So of course you can get liquid state and there is no structure. So the n size for the per psi, just per psi equal to per psi bar. You have nothing else. And if you just set your parameter just in this shaded region, you are expecting to have this solid liquid coexistent system. All right. So in the following few slides, I'm going to show you how to construct this kind of phase diagram. So you can do that either for 2D, for 1D, or for 3D, or for even in the future, if you want to have this, if you want to investigate like FCC lattices, you have to modify the free energy a bit, right? But using the same analytic skills, you can also get a phase diagram for those systems as well. All right. So before we calculate the phase diagram, let me introduce you I have already shown you like possible phases, right? But for each phase, we can analytically derive what's the energy density for each phase. And that is crucial because if we want to determine what is the ground state for the parameters that I'm using, the most simple way is basically to compare the energy of each phases. And the lowest energy one is the ground state phase, right? We're going to calculate the energy density for possible phases. For example, the liquid phase is the simplest phase, right? And the density inside just psi equal to certain constant. So I'm using the psi L bar to represent the liquid density. But anyway, it is just a constant that we assign the system. But if you plug in that insight back to the free energy, and the derivation is quite trivial because it's a constant. Every time you take a Laplacian over that, it just becomes 0. So you can see that quite easily. The free energy for the liquid state is just everything else except the Laplacian, right? And times whatever the psi is just a constant before and after that. So nothing varies with space. So this becomes just a simple volume of the system times all those are number. Psi bar L is the number you are giving to the system, and epsilon is actually the parameter you can choose, right? So it becomes a very simple function that depends epsilon and the mean density. This quantity F is an extensive quantity, but when we compare the energy of different phases, we should use a quantity that doesn't depend on volume, right? So that's defines something as the free energy density for the phases. So for the liquid phase, it's just the minus epsilon plus 1 times 2 psi bar square over 2 plus the psi bar to the 4th power divided by 4. Okay, so that's quite straightforward. If you plot how the free energy that's changing with the mean density, just a simple quartic curve, and that's it. All right. So next we can calculate the same thing for the BCC structure, right? Because we care about whether if we choose a set of epsilon psi bar, whether BCC is competitive compared with the liquid. If it is actually have a lower energy, then that should be the ground state. So as I just described, you can use this so-called a one-mode approximation, right? The density is just some constant value we are assigning to the system plus the summation of the density wave factor, density waves of the principal reciprocal lattice vectors, right? Okay, right here. But since you already know that you have those 12 reciprocal lattice vectors, they are all coming in the combination of a 1, 1, 0, right? So you are expecting, if I summation all these exponential ik dot r in 3-dimensional space, and the kx, ky, kz, all the 12 combination, if you sum together, it's going to give you this cosine qx times cosine qy plus all those two alternatives altogether. So you just do a simple summation and do a little bit of manipulation, you are getting that result. Okay. So here clearly you can see, actually what I'm assuming now is that the reciprocal lattice vector is actually q0. I'm not even saying q equal to 1, but we are going to determine what the q value is in the following procedure. So you can, in the very beginning, assume something quite general, something we don't know. We just don't know what the wave number the system is going to peak. Although we actually know that the magnitude of that should be roughly equal to 1, right? So that will kill that contribution from this square kernel. But just for now, let's pretend that we don't even know that information. Okay, So next thing, what you are going to do for BCC, you have to really carry out the integral in 3 dimensions. And you can just do that very easily over one unit cell. So if Q is the wave number, or from the n-side solution here, if you really want to repeat the structure or the one unit cell, you know the size on each side, each dimension should be 2 pi over Q, right? So clearly you see here, if X equal to 2 pi over Q, and Q cancel out, so it actually start to repeat itself. So for one unit cell, you should at least, you should integrate over from 0 to 2 pi over Q for each dimension. So the only hard work is actually to carry out this kind of integration. Once you have done that, then you know the free energy density for your BCC solid. Okay, so the integration is tedious. I mean, you can do that with a symbolic calculation. The first time I carry out the simulation, carry out this calculation, I just do it by hand. So you can do that easily. But anyway, so I'm not going to show you the results now, but conceptually, you know, the solid density basically depends on 4 things. Seems like it depends on 4 different things. Of course, we have to set what is the epsilon here and what is the mean density. So that's already 2 parameters. But also, we don't know this amplitude, right? We just say you do the summation, but we don't really know what's the amplitude. And also, we also assume that we don't know what's the what's Q here. So the free energy density actually depends on those 4 numbers, right? So the way we can solve, part of the parameter is by requesting that. Okay, so here just a quick recap of what we just what we had for the BCC solid. Okay, so here's I'm just quickly telling you that you are expecting the solid free energy depends on these 4 parameters, and when you really carry out the integral, you indeed see that the solid density depends on epsilon, the mean density, the amplitude, right? And the wave number Q here. So, it's not a trivial function, but it's still trivial in a way that only depends on those 4 things. All right. So, but now there are 2 more constraints that will give us more information about the BCC solid free energy density. Since that we are expecting that if I just have a 1 unit cell of the BCC solid, and I just let the simulation run, right? And F is the free energy of the system. So the evolution equation only brings the system toward the energy minimum. So if I wait long enough, the system should reach the minimum energy state. So which means whatever A and Q, the solid, the BCC solid takes, is going to minimize the free energy, right? Because that's the nature of our evolution equation. So that's right. So we have 2 constraints for A and Q, basically saying that the energy should be minimized with respect to Q and A. So using those 2 more constraints, we can determine the value of Q and the value of A, right? And you can see from this solid density here, where the Q appears, only on the second line, right? You don't see Q here, you don't see Q anywhere. You only see the Q appear on second line. So quickly, if you take a derivative with respect to Q, and S squared doesn't matter, right? It's something times outside. So immediately you are getting something Q has to be, very quickly, let me see. You have these minus AQ plus like 16Q to the third. Immediately you are getting Q has to become 1 over square root of 2. That's it. And as we are expecting that, if Q is equal to 1 over square root of 2, so the reciprocal lattice factor we are talking about is actually something like a 1 over square root of 2, and a 1 over square root of 2 and a 0. So when you take the magnitude of that, it gives us 1. So that's something we are expecting that's going to minimize this square kernel when we do the free energy calculation here. All right, so Q is somehow easier to get. Although we know it should be 1 over square root of 2, but we still do the calculation. All right, so since we know Q is equal to 1 over square root of 2, when we plug in here, this term just vanished. You can do the math, you can verify this term. It goes away, basically. All right. So the free energy density now is just a function of 3 parameters, epsilon and the mean density and also the amplitude. But actually we have one additional constraint that we can figure out what's the amplitude for this BCC structure in PFC. So just simply really take the derivative with respect to the amplitude. You got something like this. It's just a cubic equation. So it's a cubic equation, but you know there is a solution, a trivial solution A equal to 0. So if you take A equal to 0 as one of the solutions, then you end up with a quadratic algebraic equation, and you know how to solve that, right? Okay, so the amplitude basically equal to, you have 3 solutions. One is trivial solution 0, and the other just like those, like minus 2 over 15 per psi bar plus minus something else. Although here, in the very beginning, we are plugging the n size for BCC, like here, right? And we do the free energy calculation. But you know there's a trivial solution. What happens if A equal to 0? If you look at this BCC n side, if A equal to 0, then you recover this homogeneous state. So actually, although we are doing this BCC calculation, one of these trivial states corresponding to a liquid. Okay, so A equal to 0 is a liquid state, and you have 2 other non-trivial solutions for the amplitude. So I think you are very, very familiar with this kind of a double well pictures, right? So actually, you would have trivial solutions. So double potential, you have three extreme, but you actually only have 2 stable state. One is correspond to a liquid state, A equal to 0, and the other 2, let's call this A plus and minus. Plus is taking this plus sign. A minus is where we take this is the sign here to be negative. So you can see actually only the A plus corresponding to energy minimum, but A minus corresponding to a local maximum, right? So when we talk about, so when we get those 3 solutions, which one should we take as the BCC solid? Clearly, we should take the plus solution, A plus. All right. So what we have done so far is that we just plug in this BCC insights, but through this minimization process, we actually know Q equal to 1 over square root of 2. We also know A is what? A, we should only take this plus sign solution, and that's it. So in the tutorial session, but here is for 3D BCC structures. But you can do the similar calculation for 2D hexagonal lattices. So there you can also have what's the expected amplitude for the hexagonal structure. So when you run maybe a 2D supercooled liquid solidification problem, you can also implement few crystal seeds with this amplitude. So that's going to have a really nice simulation. You start with several seeds and they're going to encounter and form grain boundaries. But if you're doing a 3-dimensional BCC simulation, and that's the amplitude you should put in, and that is the n size for BCC you should give to the system, right? All these product or cosine you should put in. All right. But actually, although we know what's Q and what's the amplitude, so I just have those results here. You can still see here that I have to plug in back the amplitude into the free energy density, right? So then I can compare for a different set of epsilon and per psi bar, which one has lower energy. But that's a trivial calculation. You can do that numerically. All right. So, but you can see here the amplitude also depends on those 2 crucial parameters, right? The epsilon is a control parameter. Per psi bar is something you give it because it is a conserved dynamics. It's not going to change over time. So after I plug in amplitude back to the energy density, I also expect that the solid density is also a function of epsilon and per psi bar. Here should be liquid. There's a typo here. So here I'm going to show you, for example, if I'm taking the mean density equal to minus 0.3. So as I go along vertically with different value of epsilon, what the energy density of those two phases look like. So with a fixed psi bar, I'm changing epsilon as my vertical axis. So the red one is the solid density, and the black one is the liquid density, because the screen is kind of tiny for me on my laptop. All right, so you can see that for small value of epsilon, right, which one has lower energy is the liquid state. But if I'm going to higher epsilon value, I start to pick up the BCC as ground state. Of course, that's consistent with our final calculation, but I'm just to show you, if you just plot the energy density for liquid here and the energy density for solid here, that's something you are expecting to get. All right. So here we can sort of justify, without going to the density functional theory of freezing, we sort of can justify what happened as we go along the epsilon axis, right? We see this transition from liquid to solid with a fixed density. So something we are familiar with is that if we reduce the temperature, we're cooling the liquid, we start to see this liquid-solid transition. So that somehow tells us that epsilon is somehow related with the temperature. So if we do that, now the system, basically the density is conserved, right? This is the NV ensemble. But epsilon now, if we interpret that as a temperature, so now we have this NVT ensemble. And F, in that case, would be the Helmholtz free energy. All right. So you can think high value of epsilon correspond to a low temperature, and smaller value of epsilon correspond to a high temperature region. All right. How about, I mean, we can also do something else. We can, on the other hand, fix the temperature, fix the epsilon, but now we can change it for different density and see how the system changes. So that's what we are going to do that next. But at this moment, you probably can see that I always show you the phase diagram for a negative value of psi bar, right? Because from the free energy functional, you are expecting a symmetry for psi bar. I mean, the positive and negative symmetry is preserved. So you are expecting that I can actually extend the calculation to the other side. It's going to be like a mirror symmetry. But I always only show you half of the phase diagram, and just for the negative value of psi bar. And the reason now it seems to be clear that is that if we just go along horizontally, so which means if I increase the density, I'm expecting a higher density phase should be the solid phase, and a lower density phase should be a liquid phase, right? But if I'm choosing in the very beginning to show you everything on the other side, so in that case you have a higher density for liquid phase and lower density for the solid phase. So here just to show you that the reason I always take psi bar to be something negative is because of the behavior we showed here in the phase diagram. Okay, any questions so far? So here just quick summary, the solid liquid density, and let's now go along the horizontal line. For fixed temperature, let's see how the system behavior changes, right? So I'm taking epsilon equal to 0.25 here as an example. Okay, you can do the free energy curve numerically, and you see, I mean, the difference is tiny, but you can still see there's a difference, right? For a lower density, you see the liquid as the ground state, and a higher density, right, the ground state is the BCC solid. That makes sense. All right, so that's why we are marking that. So we roughly get a feeling that for certain region you can have a BCC as a ground state or the liquid as a ground state. But the next thing important is that there is a coexistent region. If we know how to solve the coexistent region, so in the future for any other case, for any other kind of the phase field crystalline, you can reconstruct the phase diagram if you know where the phase boundary is, right? I mean, so far what we are doing is that if you give me a set of parameters, I can plug into see which one has the a lower energy. But very likely, the parameter you are choosing here is something you should see the phase separation, not only the solid or liquid state, right? But you don't know that until you can solve the phase boundary for in the phase diagram, basically. All right, so now we are going to talk about how to get this phase diagram, or how to construct a phase diagram for the phase field crystal. So which means if you are in the shaded region here, you are expecting to see a phase separation. Okay, so a little bit about the thermodynamics, right? If you want to have two phases coexist, you are requiring that the intensive quantity of those two phases has to be the same. So if I set the temperature to be the same, for example, like epsilon equal to 0.25, so that's not going to change. So I always ensure that the solid phase and liquid phase, they have the same temperature. But other quantity, for example, like the chemical potential in liquid and the chemical potential of the BCC solid also has to be the same. And also the pressure of two phases has to be the same. So although you can use different techniques, but bottom line is that you're always asking that physical condition, the intensive quantity of two phases, they are going to be the same. So usually you can either do a Maxwell equal area rule construction or common tangent construction. So in the following, I'm going to show you quickly the physics, and then basically it's a common tangent construction I'm going to show you, right? So through that, the end goal is actually to obtain quantitatively where the phase boundary is. So through the exercise, we can actually draw those two lines out. All right, so here's kind of exaggeration. So here is just a schematic plot, all right, just to illustrate better the common tangent construction. All right, so here you have like a solid free energy density and a liquid free energy density, and also horizontal axis is the mean density, right? So it's basically energy density plot. All right, the common tangent construction basically ensures that the two phases has the same chemical potential and the same pressure. And the chemical potential basically, since we know F is the Helmholtz free energy, so you are taking the derivative with respect to the density, you are getting the chemical potential of each phase. So that's by definition, right? You have Helmholtz free energy F equal to mu n, then you take df dn, you got the chemical potential. So here we are doing the same thing here. If I'm requesting those two phases, right, they all have the same chemical potentials. So this is the free energy curve as a function of per psi bar. So taking the derivative basically is taking the slope of each curve. So since like the common tangent is the blue line I'm drawing here, right? They share the common tangent. So for the liquid density curve, the tangent line is here, for the solid line is here. So if you can find such a line, then on that line you are ensuring that those two phases, they have the same chemical potential because the slope is the same. But how can the common tangent, if you can find such common tangent line, how does that ensure that two phases also have the same pressure? So what's the pressure here? The pressure for this NVT system, the canonical ensemble, or the relation between the canonical ensemble and the pressure basically is that the Graham potential is equal to the Helmholtz free energy minus mu n. Let me see, I should have here. Yeah, that's right, that's right. So PV is the negative of the Graham potential. So there's a relation between all these thermodynamic quantity, right? I think you probably already know that. So if you divide by the volume of the system everywhere, the left-hand side is just the mu times n divided by v, right? The Gibbs is the mu n. And the right-hand side, the first one becomes the Helmholtz free energy density, and the second term is the pressure. So the pressure is simply what? The minus of the Helmholtz free energy density, but plus this mu times what? This is my per psi bar, right? So that's why I'm writing here, for the pressure here equal to the mu per psi bar minus F, right? So for each phase, the relation is the same. So you can write down respectively for the solid phase and liquid phase, what's their pressure. And what's this equal pressure requirement? Basically, you're saying PS equal to PL. So the equal sign gives you what? You are going to have, if those two things are equal, so mu times per psi S bar minus per psi liquid bar. equal to what? You can move the Fs to the other side, right? Or you can move the liquid to Fl to the left-hand side. So if you are requesting Ps equal to Pl, you are getting this kind of equality. It is a requirement for those two phases has the same pressure. But what is this relation? From the graph, mu, because it's a common tangent, so the mu s equal to mu liquid, what I call here is the mu equilibrium, right? So the slope is mu equilibrium. So from the graph, those 2 points, right, is the what we call the coexistent liquid and solid density. And this one is a straight line, and the miscibility gap is this gap, right? So for straight line, if I move horizontally by this distance, the energy drop would be the slope times the distance I'm moving away. So the first term basically is the slope times the density gap, and that has to be equal to the energy difference here, right? But that's exactly the Fs minus F liquid. So by doing this common tangent construction, the pressure of those two phases, they are guaranteed to be the same. So that's why you can use the common tangent. If you can find a common tangent line, then you immediately find out what is the coexistent density of those two phases. Okay? Questions? Okay, so basically, I'm just here just to saying the other same thing here. All right, so for example, so the requirement for the common tangent in terms of equation is just saying the solid chemical potential equal to the liquid chemical potential, they have the same value. And the equal pressure basically is this equation. So you have two algebra equations, right? And how many unknown variables? You don't know what's the coexistent solid and liquid density, so there are two unknowns but two equations, and that's right, you can solve that. So here just the value you can get if you just solve those two equations, those two algebra equations. So for example, for epsilon equal to 0.05, you can get those two coexistent density, etc. All right, so that's 0.05. You can get those two values very close to each other, right? Minus 1463 and minus 0.1492, so very close to each other. As epsilon goes to a much higher value, you start to see the gap become wider and wider. So roughly here's like minus 0.34, and here's roughly minus 0.31. So if you just do sequentially for different value of epsilon, you have a lot of points. In the end, you just draw the line. You have all this phase boundary showing up here. So that's how you construct the phase diagram. It is useful. Why? Because if you want to do a solid liquid coexistent problem for certain temperature, now you know which value of percent bar you should choose. You should always choose somewhere in the shaded region. But if you want to do for example, solidification in an undercooled liquid, then you should choose your parameter in the BCC region. But initially, you can set everywhere is homogeneous with maybe part of the system it has a tiny BCCC. So it will start to, the system is going to solidify, right? So, but if you are setting your parameter wrong in the liquid side, you are not going to see anything but just a homogeneous state. Okay, so that's conclude the phase diagram calculation. Once you have done that in the future, you can just refer back to the phase diagram in the paper or in your calculation and choose the proper parameter for your own project. Questions? Because we're going to move to different topic next. So let me know if you have questions. Clear? Okay. Or good? Oh. Okay. This is a 3D calculation, but you are right. Is that this is a 3D calculation? So the phase boundary I'm plotting here between the hexagonal and the BCC actually is the coexistence of BCC and hexagonal phase. But in order to have like 2D phase diagram, what I should actually construct is a hexagonal phase in liquid. So that would be some new calculation, which you will not the information you will not get from this phase diagram. So you have to really redo the calculation for 2D, but the concept is the same. All right. So let's talk a little bit about why the BCC is the favorite structure in 3D PFC, and you probably will also find out why, in the same way, why the hexagonal lattice is the favorite structure in 2D system. And once you know that, you probably have some idea about how to construct a phase field crystal for other structure, such as like FCC, like a nickel material, or for diamond cubic for silicon. So first, let's find out why in the simplest form of the phase field crystal, you are expecting BCC is the favorite structure in 3 dimensions. And it all connects back to the form of the free energy density we just calculated, or I just showed you. So you can see that this is something you will get after performing the integration, and it has certain features, right? So very quickly, you can see that if I'm setting A equal to 0, so you don't have those 3 terms, right? You can recover the liquid density, liquid free energy density. But as long as A is not equal to 0, you start to pick up contribution that in terms of A squared, A cubed, and A to the 4th power, things like that, right? But now we are taking the mean density to be something negative. So this term could be negative if amplitude is something positive. But I think you still recall that we are selecting the amplitude to be A+. So the picture I show you that of a double well potential, you have 0, A minus, A+. Actually shows you that A is something positive. So you're seeing this cubic term, or something, let's say this term, actually plays a role that basically can possibly lower the energy for BCC. You might have a question saying, how about for FCC structure? If you do the same calculation for FCC, is it possible to also get this kind of contribution for the FCC lattices? The answer is no. You only get this cubic contribution for a 3D BCC lattices and also a 2D hexagonal lattices, right? So the question is why? And you can see this term always helps to lower the energy for certain phases. So if FCC structure, mathematically, they don't contain this term. The only thing they have is something like square and to the quartic power. So in a sense, the BCC would have some age to compete with other structures. So let's see what gives rise to this term, what the physical origin of this term in our free energy. All right, so clearly you can see that if we separate the free energy kernel into 2 parts, right? The first term only contains everything up to the quadratic kernel. You have psi here and also psi afterward. That wouldn't give you anything like A to the 3rd power and the 4th power. Because only thing you plug in is using this psi plug-in here and here. All you have is only a product of A squared tops. You don't have anything else. So those high order terms basically coming from the nonlinear term. And we try to link this nonlinear term as like a competition for density waves, right? So let's see how that gives rise to this importer term that lowers the energy for BCC structure. All right, so let's focus on this psi to the 4th power. Okay, so we know for any kind of solid, the insights we are putting in is that it's a mean density plus the summation of density waves of the principal recipient lattice vectors, right? But let's just say we're just using that short notation like delta psi as this summation of density waves for simplicity. So what is this psi to the 4th power is just do the expansion, you have all those 5 terms, right? So you have things like delta psi to the 4th power, cubic power, quadratic power, etc. And what gives rise to this cubic term? There's no other choice but only focus on this term, right? Because like delta psi squared will give you something proportional to A squared, and this quartic power give you something something proportional to the quartic power of amplitude. So that gives rise to the density waves and the negative contribution in the free energy. All right, so if we do a very So if we try to reproduce the integration of this term, right, and we only focus on one of those 5 terms. So in this integration, what we are getting is you have this 4 cancel with this 1/4, but you are doing this integration with like per psi bar times delta per psi to the cube. And this delta per psi to the cube, now I just use the original notation. It's a summation of the principal received lattice vector, the density wave of all those received lattice, all those density waves. So, but this product, right, you have all different density waves. So the first one is summation over k, but the second and third one will be summation over k prime, k double prime. Because k here is just a dummy variable, but in any case, you should sum over those 12 reciprocal lattice vector for BCC. So when you do that, you can see that basically is just a triple summation, and you can put together all this exponential IKR or n times exponential IK prime dot R and also the exponential IK double prime dot R, right? And you can collect all the K here, become K1 plus K prime plus K double prime. But immediately you recognize this formula, and you immediately know that if K plus K prime plus K double prime, if it does not equal to 0, when you do this integration over space, it's going to be an oscillatory profile. And if you integrate something oscillatory profile over an extended system, the plus sign and minus sign is going to cancel out each other. So if the summation of these 3 wave vectors does not come up to 0, then the contribution here basically is approximately equal to 0. So the only thing that's left is actually when the summation of those 3 wave vectors equal to 0. So here you have this Kronecker delta function, right? If k plus k prime plus k double prime equal to 0, then you pick up 1. Otherwise, you pick up something 0. So if that's 1, you do the integration, you got this volume here. Okay? So this integration is actually become trivial now because it's just equal to the volume times those triple summation. But when you do those triple summation, you're actually trying to do is to adding different wave vectors in the reciprocal space and to see how many combinations of those FCC lattices can sum up to 0. So for example, you can have 1, 1, 0 plus 1 bar 0, 1 and the 0, 1 bar, 1 bar. So you can do that, you can get 0. So that will contribute at least 1. So you can keep listing all the possibilities. So guess what? How many combinations you could have in the end if you do all this kind of counting? I mean, it's a non-trivial problem, of course, but you are expecting to get exactly this coefficient, 48, right? Because we are saying this term is coming from this integration, and the integration in the end is just simply equal to how many combinations you can have of those reciprocal lattice vector for BCC. You can pick any 3 of them and form a closed triangle, right? To have this k plus k prime plus k double equal to 0. So exactly, if you write a simple code or really sit down and draw the graphs, you can have like 48 possibilities. So that gives you this coefficient. Okay, so that's why you will have a non-vanishing cubic term for the BCC structure, and that somehow is going to lower the energy for BCC. But as the question we proposed before is, how about the FCC structure? So for FCC, what you are having is the reciprocal lattice vector is all the plus minus 1 combination. So there's no way you can put 3 of those vectors and get 0, right? For example, if you have 1 something something, the second one you try to put a minus 1 something something, but third one always give you 1 or minus 1. So when you sum the x component, you'll always get some contribution. So there's no way you can get 0. So that's why when you do a calculation for FCC lattice, you can repeat putting the n sides for the FCC solid and do integration to get this free energy for FCC. You wouldn't have this cubic term. So you only have a quartic term and quadratic term. But compared with BCC, you have this cubic term. And because of this term, it gives an extra edge for the BCC to compete its energy with other structures. So immediately you can think about in 2 dimensions. You have triangle lattice, right? So you have like in 2D, 6 wave vectors. They are all 60 degrees apart. So quickly you can say, let's pick one in the horizontal direction. The other is 120 apart. So you are summing those two. And what you are getting is a vector in a 60 degree. But now you just pick the third one as the one in the third quarter, summing all those 3, 120 degrees apart. You immediately get 0, right? So definitely for 2D hexagonal lattice, you also have this kind of term that will not vanish. So that's why in 2 dimensions, it's much easier to get a hexagonal lattice. And that's also true for all the, not all, but for many natural phenomena, right? You usually see hexagonal symmetry occurring somewhere like even in the sky or in a sand dune, the pattern formation, right? You can, or the fairy circle I just showed you yesterday. In the area, there's a land, you see larger circles. If you see from the satellite photo, you will see a very nice arrangement for these hexagonal lattices. But here's one simple explanation that for this kind of symmetry, it always has a little bit better edges against other structures. All right. Okay, so no questions? Okay. If there's no question, let's move on to 2 dynamical equations I would like to show you what you can do not only with this conserved dynamics, but in order to speed up your calculation, you can also use what we call a non-local conserved dynamics. Okay, so the reason sometimes you would probably will need this kind of evolution is because usually for the PFC equation, it is a diffusion type equation. So which means if the delta F delta psi has variation in space locally, then it's going to induce the flow, right? So that's going to give rise to the change in the psi locally. So the diffusive type equation is always going to change things slowly, only locally, right? So that is going to give you something realistic. I mean, physically, right? You are expecting like a mass should diffuse from one place to the other place slowly. But what happens if you just want to, for example, simulate a solid liquid interface at equilibrium, right? You can, of course, set up your system on one side is a BCC solid, the other side is liquid. And you can just wait for quite a long time to see this interface forming. But what happens if initially you are setting slightly off what's the liquid-solid coexisting density? If you are setting something off, it's going to take a really long time for the solid density or liquid density to diffuse to each other, then reach the final equilibrium, right? So let's say if we only care about the equilibrium picture, we don't care about the kinetics, right? We'll just wait long enough to get the final equilibrium state. We don't really need this local diffusive picture. We can just use something non-local, but still, I mean, we are requesting to have the density to be a conserved quantity. So that's something I'm going to show you. And that's actually being shown in 2008 paper. That's something you can refer to more detail. So the advantage is that you can get your simulation to the equilibrium much quickly. Then from there, you can measure whatever the equilibrium property you would like for the system. Okay, so let's derive a little bit what's the evolution equation look like. And that's something you can also do in the tutorial session, right? So you can have different kind of dynamics ready. And maybe, I mean, in the following, we are going to talk about the physics about the solid-liquid interfaces at the equilibrium. So for those simulations, this kind of evolution equation actually helps and save a lot of time. Well, that will save you a lot of time. Okay, so To get this non-local conserved dynamics, of course, now you're trying to have a constraint on the system, right? One extra control of the system. So mathematically, you can use something we call a Lagrangian multiplier, something well known in mechanics. So what is this constraint? We are trying to conserve the density, which means if I'm setting the mean density to be per psi bar, then per psi bar integral over the space minus whatever it's involving has to be 0. So that is my constraint. It has to be true always, right? So a typical way of implementing the Lagrangian multiplier is just saying that you have something before, you have this free energy functional, right? But that is the functional without the constraint. So what you can do is to add something extra to the original free energy functional, right? So I'm adding a constraint which is 0 to the free energy functional. So it's not going to really change the value of the functional. And I can adding that with certain any kind of coefficients, and that coefficient is our Lagrangian multiplier. It's something that hasn't been determined yet. But by doing so, actually the system is going to preserve the density of the system. It's not going to change over time. So that's how you can implement an extra constraint in your system. So you're using the original free energy functional, but you're just adding a constraint to the free energy functional. So now the non-local dynamics, because in non-local you don't need this extra Laplacian in front. And of course you're probably familiar with this kind of evolution equation is going to bring the energy toward the minima as well. So just use the short notation that the chemical potential mu here I'm referring to is the original free energy taking a functional derivative with respect to per psi. So that will be just the first term taking the functional derivative. But the second term, if I'm taking the functional derivative with respect to per psi, right? The first term is just constant. It doesn't contribute anything. But the second term is going to give me 1. But there is a coefficient, Lagrangian multiplier here. So that's my mu L. So it seems trivial. I mean, you seem just to have to run whatever you have before, but you just take off this Laplace in front. But in the Fourier space, you just don't multiply by minus k squared in front. But in addition to that, you need to know what is this value, this multiplier, right? So the next thing is, how do we know what value we should add here? If we know that, we just run this evolution equation, and it's going to preserve the density. It's not going to change, but in the meantime, it's going to speed up my simulation. All right, so how do we determine the mu L? Because since we are requesting the density to be conserved, so we are requesting that the per psi, the integration of the whole system over time should not change. We're requesting this to be 0. And how do we get that? So the evolution is here, right? So basically, I'm doing integration over space on this equation. So the left-hand side will be the partial plus that partial d doing the integration over space. So that would give me the left-hand side right here, right? And I'm also doing the same thing for right-hand side. So that would be the minus mu plus mu L and doing the integration of the space. All right. But since the constraint is saying we shouldn't have any variation of this quantity, so this quantity equal to 0. So what is mu L? So mu L basically is what? So you just moving things around. So mu L is just a constant. So mu L times the volume equal to what? Mu doing integration over space. What is this chemical potential? That would be this kind of stuff, right? It's the del F delta phi. So right here. So I'm just writing the final results. So the mu L, although is a number, but it requires what you need to calculate this quantity for every time step, which is some function of per psi and doing an integration and divide by the volume. That's it. But it is not that bad. I mean, you might think that you have to also work out what's the Laplacian or the Laplacian square, things like that, and operate on the Psi. But you don't need to worry about that because, once again, if we are working a system with periodic boundary conditions, so anything that's with this Laplacian, you can use the divergence theorem to show that those term vanishes. So actually, you can just ignore anything taking the special derivatives. So you are actually only need to evaluate what? Minus epsilon plus 1, the thing times Psi, plus the Psi cube doing the integration. Okay? So for each time step, you have to evaluate this chemical potential and plug in here and run the time evolution. Right? And since the dynamics is not the locally diffusive dynamics, so everything can reach equilibrium much quickly. So that I would suggest that's something you should do if you are working on this, for example, solid degree equilibrium, or you're starting like polycrystalline, right? And you just want to see how the dislocation is going to distribute in the end. You don't really care about the kinetic in between. Then in that case, you can use this kind of method to speed up your simulation. All right. Okay. But since in the tutorial session, we are doing everything in the reciprocal space, right? So in that case, we don't really care about, we don't even need to carry out this integral. Yeah, because this is just a number. So what we are doing is saying a partial Psi over partial t equal to something plus a constant. So the concept of doing the evolution in the reciprocal space is by taking the Fourier transform of everything, right? And those constants only will contribute a term in the k equal to 0 dynamical equation. So it's saying the Psi 0, let's say Psi 0 corresponding to the Fourier amplitude for k equal to 0 mole. So you're saying how the DC mode is going to evolve, and that is the only coefficient will be affected by this mu L. But Psi 0 basically is the mean density, and we just don't want that change. So you're just saying for k equal to 0, that is not evolve that term, and that's the end of story. Okay. Or if you really carry out the calculation, you will find out that partial Psi, partial t for the k equal to 0 mole is exactly equal to 0. So once you finish that calculation, that will give you 0. So for the spectral code, it's actually very easy to implement. You just redo whatever we are showing you yesterday, but for the DC mode, for the k equal to 0 mode, you just say there's no evolution for that coefficient. Okay. Okay. So things goes much more smoothly as I expected. So I think I'm in probably the last slide already for today. So let's talk about something else about how we can extend the PFC to a grand canonical ensemble. So which means we're trying to fix the chemical potential and doing a simulation. So fixing the chemical potential for the system means that the system is in contact with particle reservoir, right? So the system is trying to fix that so particle can come in and come out. All right. So one of the example you might need this kind of dynamics is that you want to do solidification, or you want to study how the solid liquid interface is being driven by some driving force, for example, like chemical potential difference, but not in this case, but that could be also a pressure difference. Okay, so the following I'm going to actually show you that if we make the chemical potential to be a constant, so in a PFC, actually what drives the solid liquid system out of equilibrium is actually the pressure difference in the solid and liquid phase. All right, so that's what I'm going to show you next. But just bear in mind that the potential application could be the solidification plot. Okay, so again, we are using this schematic plot. All right, so I'm also showing you a reference common tangent line, right? So that's if we are setting the mu to be the mu equilibrium, I can also use this kind of dynamics to simulate equilibrium solid liquid interface. So the interface is not going to move at all, just stays stationary. But if we want to move away from that value to have something different, for example, let's say if we try to run a simulation with chemical potential mu f, right? So one possibility is that the mu f is actually a tangent line at this point, right? So if I'm choosing a different mu, which means a different slope line. So this kind of slope will, the tangent line will in contact at with the solid density curve at this point. But you can also ask the same thing. If I'm trying to draw the same slope line, where it's going to in contact with the liquid line. So I'm going to show you that as well. So that's roughly this point, right? So if I just setting a different chemical potential, it's going to be tangent with the solid density curve right here, and also the black curve, the liquid density curve right here. All right. So what is since those two phases, they are forcing to have the same chemical potential. But now we can evaluate a bit what is the pressure in the solid state and the liquid state. So we have seen this before. The pressure of the solid phase is the mu times the density minus the Helmholtz free energy density. So the same thing happens for the liquid phase, right? Right. But now we are actually using the mean density as the value where the tangent line is cutting each energy curve. So that would be this precise liquid here and the precise solid here. All right, so that's also the Fs means the solid free energy here, and the F liquid is the liquid free energy here. Right? So since we are enforcing the system to be run at certain chemical potential, and that chemical potential is not the equilibrium chemical potential. So although we are enforcing those two phases has the same chemical potential, but the pressure is going to be different. So one way to evaluate or to estimate what's the pressure difference, you just take those two things and subtract from each other. So Ps minus P liquid, for example, will give us the forcing chemical potential times the density difference, and minus also what's the free energy difference between the solid phase and liquid phase. Okay, so what we are having here is that, for example, minus, so where is the FL? I'm marking here, right? Because it's the point at the tangent line here, right here, right? So that's my FL, the liquid free energy density at this contact point. But the other thing is, what is this FL plus the slope times the energy difference? So I know for a straight line, from here to here is a straight line. So the value y here times the slope and also times the distance jump from here to here will gives me the energy, the drops of y. So combining those two terms is actually the two terms underlined in the orange color will actually give me this value. So which means is the intercept of this black dashed line to the value right here at psi equal to psi s. So that value subtract by this Fs. Fs is just right here. So delta P actually is what? Is actually the gap between these two dashed parallel lines. So that is our pressure difference. So when I enforced my simulation at different chemical potentials, through this way you can just draw the tangent lines and see how big is the gap between those two tangent lines. And that's going to be the driving force or the pressure difference between these two phases. And the larger the pressure, and you are expecting maybe a faster growing of your faster growing or melting depends on the system is preferring to perform a solid state or liquid state. All right, but usually you will see the interface move faster as the driving force is stronger. All right. Okay, but note that the pressure is related to the grain potential energy, right? We know grain potential, usually we use the symbol like omega. Omega is equal to minus PV. But if we are talking about a grain potential density, so that's minus PV over V. So omega is just equal to minus P. So this density gap is actually minus the difference in chemical potential, but with an extra negative sign in between. All right. But why do we care about the grain potential? because we want to see if we have a positive, then if we have positive pressure difference, will that cause the system to melt or to solidify? That's something still remain unclear. So it's important to actually connect this pressure difference with the grain potential density difference, right? So actually, the relation is that if the delta omega is greater than 0, so what is delta omega? The delta omega is the grain potential difference between the solid and the liquid, right? So if the solid grain potential is higher, that's what I mean, right? If it's higher, then it's not a preferred state, so the system is going to melt. But in other sense is that the delta P is less than 0, then we should expect the system to melt. But on the other hand, if delta omega is less than 0, then you are expecting your solid is going to grow to solidify. So in this case, clearly we have something positive, right? So which means delta omega is something negative. So in this case, we are expecting the system to solidify if we are choosing the mu like I'm showing here. And it sort of makes sense because previously, the common tangent line, which means the blue line, actually have a preferred liquid density here and solid density here. But since now I'm enforcing a new chemical potential, the preferred density for either the solid and liquid, they all shifted to a higher value. So the system is more packed, right? So even from there, we are expecting, if we are using this kind of chemical potential to run the simulation, the system is going to solidify. All right, so here's just the concept, right? So what's the evolution equation look like? I haven't shown you yet. So that's our final step. So since we know the system is going to minimize free energy, but now we have this grain canonical ensemble, right? It's a mu Vt ensemble. So we are not going to minimize the Helmholtz. We are going to minimize the grain potential, omega here. And we know the grain potential and Helmholtz free energy had is omega equal to F minus mu n, right? So, but the density here is just the integration of psi here. So, similarly, if we want to minimize that, the evolution equation is simply using this relaxation dynamics. You have partial psi, partial t. But on the right-hand side, we are just replacing with minus delta omega over delta psi. So I'm taking functional derivative of this on my right-hand side here. So the first thing will give me the delta f delta psi. The second term will give me this mu f here. Right. So just in terms of the evolution equation, it's quite straightforward. You just enforcing whatever mu you would like to have here, then you start to see the interface is moving either toward to solidify or the solid is going to melt. All right. Any questions? All right. So that's basically the material I have for you today. So let me recap that real quickly what is going on in today's lecture. So mainly I would like to show you layout how we construct the phase diagram. And you can use that technique to construct the phase diagram for whatever kind of phase field crystal modeling you are dealing with. But the concept is always to get the free energy density for different phases. And to see whether they can coexist, you have to carry out quite standard thermodynamic procedure to do a common tangent construction or the Maxwell equal area construction. That's something you can find in Professor Elder's paper. That's typically some other people will do to obtain the phase diagram. Myself, I usually prefer to use the common tangent because you can see that a little bit clear from the graph and to see what is the chemical potential and also the pressure. So that's why I prefer to use this common tangent approach. But you can also use this very classical Maxwell equal area construction as well. So with that, I think it's going to help you to determine the proper parameter you are going to use in the simulation. And we also talk about why the FCC is something it's not that easy to get in PFC. But with that in mind, you know what the difficulties, then you can find a way to cure that problem. And actually, people have already made some progress in that front. I have a paper with Professor Karma addressing that issue back in 2010. So we proposed a two-mode model, two-mode PFC model that can give you the FCC structure in 3 dimensions. And also in 2D would be a square lattice, because you would expect for square symmetry, there's no way you can have 3 factors to give you a closed triangle. You always have all the 4 reciprocal lattice factor, right, 90 degrees apart. So for 2D, the square lattice is not a preferred pattern, but with the two-mode model we proposed back in 2010, you can also get a square in 2D and an FCC in 3D. So in addition to those, we talk about 2 other different kind of dynamics. I think that's going to help to a certain degree to your material science project. All right, so that concludes my lecture today. Any question I can answer? Oh, minor PV? Okay. Probably here is, you can also see that the Gibbs and the Helmholtz free energy is equal plus PV. That's the relation, right? So the Green potential is, or the other way you can think it, the Green potential can be also written in terms of F minus mu n. So you shift everything the other side. So you can find this thermodynamic relation. Actually, this is the negative Green potential. But the question is, you are asking why, or okay? Let me see if there's a simple answer to that. Okay, well, it's an answer, but I'm not sure that's the best answer. All right, so you know we have different kinds of thermodynamic free energies, right? And the relation between them, they are basically is a simple Legendre transformation. Depends on, for example, if I want to go from the Helmholtz to the Green potential, because canonical ensemble or the Helmholtz is NVT ensemble, but Green potential or the Green canonical ensemble is the mu VT. So if I want to change from number of particle to fixed camp potential, I need to either plus or minus mu n, right, to do a Legendre transformation. All right. So you can start from there and write down in the very beginning what's the Helmholtz free energy, what's the easy relation with the internal energy, is the entropy temperature. I think it's, as I remember, I think F equal to U plus Ts minus PV plus mu n, right? Okay, so next you start to subtract terms to get Green potential, right? So you have to use F start to plus PV, plus mu n. So with the very beginning of that definition, you just keep doing the Legendre transformation. In the end, you are going to find out the only thing you left is minus PV. So roughly you have already see the structure. You see the Helmholtz free energy equal to U plus Ts minus PV, things like that, maybe, right? So there's already minus PV there. So something else you are going to do next is to plus and minus mu n. So you are removing mu n. So the only thing I might mistaken is that it's actually U. I think it's, let me see. Do you recall the relation what I was referring to? I think it's F equal to what? U minus Ts. Okay. So what is U? U is like Ts minus PV plus mu, right? So if you just do the first step, U minus Ts give you Helmholtz. You already remove the Ts term. You have it's only 2 terms, minus PV plus mu n. Agree? And now you do the other Legendre transformation, minus mu n. So you remove again 1 extra term. So once you have already done those 2, you remove 2 terms. The only thing left is minus PV. But the reason we are doing that transformation is trying to get from the very beginning the internal energy to the Green potential. So the only thing left is what you are getting is actually the Green potential. So that's one way to quickly see why omega equal to minus PV. But I think there might be a much physical way to understand for sure. Yeah. But that's a quick answer, I think. Okay, all right.
Okay, so let's try to do this exercise. Yeah. So what we do is we start with the diffusion equation. For simplicity's sake, I am going to do it in 1D, okay. And you can consider any concentration profile, and any generic concentration profile can be written as a summation of sines and cosines, okay. C is obviously a function of x and t, right. What I am going to assume is that it has an amplitude which only depends on t, and you take summation of all k's. So, for different case, different amplitude you give, then you will get any random composition profile that you take. So, this is basically to prove that this equation is going to tell you that composition will get homogenized, right. That is what we want to prove. If you take a sinusoidal profile, it is going to become flat, that is what I want to prove. There is a way to look at it, you can put a sine itself, but we are doing it a little bit more general by putting a ak exponential ikx. Because these sine waves and cosine waves are independent, we can do it for 1k and we can later sum it up for all k, they just add up. They add up only if you have linear terms, and that is why we are going to linearize if there are non-linear terms, but in this case this is a linear thing, there is no issue. So, let us take a particular A and substitute here. So, you have dou by dou t of ak, which is a function of t exponential ikx, right, on this side, and you substitute here L squared by del x squared is only going to operate on this, and it is going to give 2 ik's. So, you are going to get minus dk squared ak exponential ikx, right, because ak is only a function of t. So, that is not affected, and this del squared by del x squared operates on this, gets a minus ik minus ik. So, minus ik whole squared, that will give you minus k squared. And because this dou by dou t will only act on ak, and ak is only a function of t, so you might as well write it as dakt by dt is equal to this exponential, and this exponential you can take off. Right. So, now you can see that this can be written as dak of t by a is minus dk squared t. I have taken dt here, I have brought a here. So, everything on this side is a, everything on that side is t. You can integrate. This is dA by a. So, logarithm of a is minus dk squared, sorry, this is the dt here, becomes dt. So, you can see that now the solution a naught as a at time t equal to 0 what does k represent? Right, you have different wavelengths, this is the wave number, k squared is positive, time is positive, diffusivity we always assume as positive, if so this is negative. So, any wave whatever be the amplitude with which it starts, it is going to die down. Okay. Another way to think about this is to consider a sinusoidal profile. This is curvature. Okay. So, because it is negative, it is going to die, because curvature here is positive, it is going to grow. So, with time, so how the composition changes with time is basically given by the curvature. Assuming D is positive, then the sign of curvature will decide how the system will evolve, and so this will go down, this will come up, so everything will become constant. So, this is known as homogenization, and the argument that we are making is by looking at a stability analysis. I take waves of different wavelength, and if I give it to this system, what happens to it? That is what I am looking at, right. Now, where is the linear stability analysis is coming from? And you can see that this stability analysis has to be a little bit different if I modify and write the Cahn-Hilliard equation, for example. Okay. So, let us do that exercise. This is very common, this is derived in many textbooks on diffusion, phase transformation and so on. So, this you might have seen, but this is the rate of growth of amplitude, okay, right, and that depends on the sign here, because all the quantities are positive, this happens to be negative, then that wave will not grow. Now, let us do this other exercise. This comes from the classical spinodal, where in some regions it looks as if D has become negative. If so, then this becomes positive, then that wavelength will grow. But the problem is, because k is wave number and larger wave number will have, so it will keep giving you growth, and it will give you growth for small wavelengths which are larger k's to grow much faster, okay. So, if you take the classical diffusion equation and put diffusivity to be negative and look at what happens to the solution, you will see that any wavelength grows, and the smallest wavelength that you can support on a lattice is basically the wavelength of the order of lattice parameter, and if you have composition waves of the order of lattice parameter, what you get is an ordered system, right. I take a NiAl B2 structure, for example, one layer is Ni, the other layer is Al, then other layer is Ni, and so on. So, which means you start with a system which is supposed to undergo spinodal decomposition, because that is where we think that diffusivity has become negative, and so if you put it there, you get a solution which gives you ordering, which is not consistent, because spinodal and ordering, if you consider a regular solution model, should give you totally opposite kinds of interaction parameters for the EAA, EBB and EAB, the bond energies. So, we assume that it is a phase separating system, which means EAA, BB bonds are preferred, and you put this solution into the classical diffusion equation. If you make the only modification that the diffusivity is negative. The way that modification is done is by saying that, in other words, okay, so the typical argument that is given is diffusion equation is empirical, it is not valid. The right thing to do is to take the mu is the chemical potential, and mu can be shown to have this, I mean D can be shown to have this, okay. So, depending on the curvature of the free energy with respect to composition, then D will pick a negative sign, and in that case, if you have a profile like this, this will start growing and this will got decaying. So, you will get a solution like this, okay. So, if your explanation is only that chemical potential is the right thing to do, even then if you put it back into this equation and solve, you will find that this grows, but a smaller wavelength grows faster than this, and so the smallest wavelength that you can support, which is basically lattice parameter distance, will give you ordering as the solution. So, it is true that the right equation to look at is one where chemical potential gradients are to be considered for diffusion, but that alone is not sufficient. That also leads to a problem. So, you need to change the free energy by incorporating the interfacial energy terms, because the diffusion equation is giving you that solution saying that it is alternating AB layers, without realizing that you make AB layers, there are AB bonds and those are costly, and we have never shown to the system in this chemical potential that there is such a contribution in classical thermodynamics. That is the reason why you need to change the free energy itself. Okay. Now, the way we change the free energy is by saying now that this mu is the variational derivative of the free energy with respect to composition. Variational derivative because now the free energy is a functional, okay. F by NV let me consider, so that the diffusion equation I do not have to worry about NV factor. So, F by NV is dV, and then we have a double well potential typically. So, and that is okay, you should not confuse with this A, this is the A well, C squared into 1 minus C whole squared plus kappa, right. Now, how do you take the variational derivative? So, let me write it in (1D), okay, not writing in multiple dimensions. So, then it is, let us call this as F0, this term. So, that is 2 kappa this you will put equal to 0 in the Euler-Lagrange equation, but we take this as the chemical potential and put it here and evolve the system, that is the Cahn-Hilliard equation. Okay. If you have and this if you do, it is 2 AC 1 minus C 1 minus 2 C, and assume that this kappa is not concentration dependent or position dependent, then you have 2 kappa del squared C by del x squared m del squared acting on this is dou C by dou T. Now, I can do the same exercise. I can say that C is equal to sum AK exponential IKX. It is called linear stability analysis because in this term now we will only consider the linear term. Non-linear terms will lead to mixing. Okay. So, it is valid for very early stages where composition changes are so small that C squared, C cube etc. can be neglected. At that early stage what happens is what linear stability analysis gives. So, you will get, so you can see del squared and there is a del squared. So, this also should be dou squared by dou x squared for me. So, you will get a del power 4 term here, and with the appropriate sign if you do the analysis you will get a growth rate where this term for very small wavelengths it will start giving the opposite behavior, it will not allow it to grow. So, because of which if you draw the k versus growth rate, right, if you look at, then you will have a curve which looks like that. There is a critical k above which it grow, below which it will not grow. Critical wavelength, smaller wavelength will not grow, but there is a larger wavelength limit that is set. Okay. And then the maximally growing one will be the one that you will see and so on, but that is only for early stages. But if you go to later stages, this is also seen experimentally that you will pick one wavelength if you are doing some neutron diffraction, but as time proceeds the structure will coarsen and the wavelength will shift. But the early stage you can get the wavelength that would be picked by doing this kind of analysis. What was done yesterday was a linear stability analysis of this type, but with 2 variables in 2D. Okay. So, this is just to give you a background to what the linear stability analysis is, and it is a very common analysis to analyze things like this. Perturbation analysis also, you can think of it as also a perturbation, that you take I can do a C0 plus a very small fluctuation and do the same thing. I mean, C0 is a constant, all that will go away and you will get pretty much the same result. So, the stability analysis or perturbation analysis depends on how you are considering this disturbance that you are giving. In diffusion, typically we do not consider that as a perturbation, because we say random concentration profile you can put and it will homogenize, which is what will happen if you throw your sample, solidify and then you want to homogenize, you throw it in the furnace. It could be any random concentration. Given enough time, it will homogenize. That is what Fick's law tells you. But you do not, sometimes you do not do that, you do not take arbitrary amplitude, but you take some, like spinodal for example, we take some C0 about which we give a small disturbance and see what happens to that disturbance. If you are in the miscibility region, they tend to grow. If you are outside of it, they will get killed unless the fluctuation is sufficient to overcome the barrier, then it will become nucleation. Right. So, these are the 2 mechanisms. So, you show that spinodal happens even if there is very small perturbations. Okay. Okay. So, most of you would have seen, but if some of you have not seen this, you can go to my NPTEL lecture on phase field modeling, where I have done it in greater detail and shown, but this is basically the idea. Okay. Which kind of curve? This kind of curve. So, many a times you will see that whenever you are trying to see the growth rate of many of these disturbances or composition fluctuations and so on, see what is this limit? K equal to 0 is lambda is infinity, right. That means, if something has to happen diffusionally, like Kwon said, it can be a non-local one, then everything can happen in one go. That is not physical. If it has to happen through diffusion, then you see that long wavelength means diffusion is going to take very long time, right. Very short wavelength typically means that your interface is very jagged. Interface is very jagged means large interface area, which means it is very costly for the system. So, typically you will see that this also is very costly for the system. In between somewhere here it will peak. This is a region where the kinetics is dominating. This is a region where you can say energetics is dominating. So, somewhere in between is where you will see. So, this curve is very common. If your physics is that kinetics has a say on the long wavelength side and energetics has a say on the short wavelength side, which is what most of the times we see, you will always see a curve of this type. Okay. So, that is one way of understanding why this curve looks like that. So, the growth rate here is positive, but it is close to 0 because it is going to take so much time, and here it is negative. Somewhere in between it will peak, and that will be the typical wave that will be chosen. That is called the maximally growing wave. Okay. Of all the waves, that has the largest rate of change of amplitude, because see, we are only looking at dou A by dou T, right, A dot, which is telling you how fast this amplitude is changing. Any question? Okay, very good. So, okay, so we will stop here.